In this module, we're going to talk about the next step in our understanding of quantum theory and the electron and the atom. And we're going to talk about this phenomenon called line spectra and how this guy Niels Bohr came up with a model of the atom. So here's the idea. If you take regular white light, just regular like an incandescent light bulb or sunlight, pass it through a prism or a diffraction grating, you'll get what we call a continuous spectrum. You've seen this. Looks like a rainbow, right? All the colors of the rainbow. But if you take a gas discharge tube, basically what that is, it's just a glass tube that's been filled with just one type of gas. It could be hydrogen, it could be neon, it could be, anything, really anything, any gas. But, and this glass tube has electrodes, just a piece of metal on each end. And if you hook these pieces of metal, these electrodes, up to a power supply and turn on that power supply, the tube will glow. This is what you see when you see the neon lights in windows. But anyway, when you take the light that comes out of this gas discharge tube, and we'll just use hydrogen because that's the simplest really, and pass that through a prism, instead of seeing a continuous spectrum, all the colors of the rainbow, you only see certain lines. You see only certain colors, certain wavelengths of light. Hydrogen, the ones that you can see in the visible region are 410, 434, 46, and 656 nanometers. This is called a line spectrum. And scientists back around the turn of the century, in 1900, were unable to explain this using classical mechanics. So then along came this guy Bohr, who proposed that just like Planck said about energy being absorbed in quanta, and Einstein said about the energy being quantized, he said, well, what if the electrons in an atom could only exist in certain orbits about the nucleus? So if this is the nucleus, then he's saying that an electron could exist at n equals 1. We label these orbits with n, 1, 2, 3, and so on, or 2, 3, 4, 5, and so on. Now, because the nucleus has a positive charge and the electrons have negative charges, there's an attractive force between them. It's Coulomb's law. And before Bohr came up with this hypothesis, scientists were unable to explain, amongst other things, why the electrons didn't just fall into the nucleus. And Bohr said, well, what if they're just not allowed to be anywhere but in these orbits? So if we take a slice through the atom and we can see these circles, remember in real life it would be a three-dimensional sphere, but an electron can be here, 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 or anywhere out to infinity, but nowhere in between. And electrons, he said, can transition between these orbits. They can go from a low n to a higher n. In order to do that, they'd have to absorb energy because you have to pull them a little bit away from the nucleus, and that's hard to do because the nucleus and the electron have opposite charges. But they can also fall down from a higher n to a lower n, and when they do that, they release energy. Okay? And we'll see that comes out as a photon of light. This picture over here is showing the relative energies of an electron in a hydrogen atom, and the spacing of these lines is more accurate than this picture is over here, because as you get farther from the nucleus, as n increases, the energy levels or the lines get closer and closer together. So the difference in energy between n equals 5 and n equals 4 is a much smaller energy than that between, say, n equals 2 and n equals 1. And so the way that Bohr's model explained line spectra is that if the electrons were only allowed to exist in certain orbits, and when they would fall from a higher n to a lower n, they would release energy in the form of a photon, and that photon would have to have the same energy as the difference in energy between the energy levels in the atom. So, if an electron fell from n equals 2 to n equals 1, the energy of that photon would be equal to the difference in energy of an electron at n equals 2 and n equals 1. We'll see the equation that Bohr came up with in just a moment. By the way, in the hydrogen atom, we say that when the electron is in the n equals 1 orbit, it's in the ground state. Let's see here. In any atom, though, the ground state just means the electron is in the lowest energy orbit that it can be in. And if in the hydrogen atom, if an electron were in a higher energy orbit than the n equals 1, that we would call that an excited state. And there's multiple excited states. Let's say there, for example, or there, for example. One last thing about this picture, there's in the hydrogen atom, there's only one electron, but there are an infinite number of orbits. Of course, as they go up, they rapidly get really, really close together in energy. All right, so here's Bohr's equation. Bohr derived this equation that describes the energy of an atom. And he says that the energy of an electron in an atom is negative 2.178 times 10 to the minus 18th joules times z squared over n squared. Now, z is the nuclear charge. That is the number of protons. Now, if it's a hydrogen atom, z is equal to 1. And so it's just, 1 over n squared. But if it's a hydrogen-like atom, this equation also applies to hydrogen-like atoms, then z can be something other than 1. What does it mean to be hydrogen-like? It just means that that atom has only one electron. Now, for anything other than hydrogen, we have to remove electrons from the neutral atom in order to have just one electron left. So, for example, helium, the neutral helium atom has 2 electrons. If we take one away and make the helium plus cation, it's hydrogen-like. Neutral gold has 79 atoms. If we were to take away 78 of those electrons, it would give it a positive 78 charge. Then it would be hydrogen-like. And in that case, z was not going to be 1. If we were using this equation for gold 78 plus, then because there are 79 protons in the gold atom, z would be 79. We have 79 squared here. This right here is a very useful form. You will use this form of the equation, Bohr's equation, a lot. This describes the difference in energy of an electron in an atom between 2 different levels, n final and n initial, when it transitions from n initial to n final. Remember, these n's can only be integers, 1, 2, 3, 4, 5, etc. And so the change in energy of an electron in an atom is negative 2.178 times 10 to the minus 18th joules times z squared times 1 over n final squared minus 1 over n initial squared. Memorize this equation. Put it on your card. You will need it. Remember, if it's hydrogen, z is 1. If it's a hydrogen-like atom, then z is the number of protons in the atom. The other thing, another form of this equation really, is when we're talking about ionization. To ionize an atom means to remove an electron. If it's a hydrogen or hydrogen-like atom, that's only one electron, so we're removing its electron. And so to ionize an atom, the way we describe that is we say n final in this equation goes to infinity. Now, if you take the limit as n goes to infinity over 1 over n squared, it goes to 0. And so basically this term goes to 0. And we get the change in energy, the ionization energy for a hydrogen-like atom is just it simplifies to z squared times 2.178 times 10 to the minus 18th joules over n initial squared. This term goes to 0. And the negatives cancel, and we get this. So, good equations to know. All right. So, like I was saying, when an electron drops from a high end to a low end, it loses energy, and that what the energy does is actually creates a photon. It makes a photon. That energy is converted into a photon, and the energy of that photon matches the energy lost by the atom. This is called emission when this happens. An emission spectra we can talk about. On the other hand, when we can also excite an electron in an atom from a lower end to a higher end. It has to gain energy to do that. And where that energy comes from is by annihilating a photon, by absorbing it. And when that photon hits that atom, the photon is annihilated, and the energy of that photon goes into exciting an electron in that atom from a low end to a high end. This is called absorption. I think that's a P, isn't it? I'm not sure. It doesn't matter. And so we say that the change in energy of the atom is equal to the negative energy of the photon. Okay, well, all this means is if this is an absorption, then the change in the energy of the atom is positive and the energy of the photon is negative. What does that mean? It just, because negative times negative is positive. It just means that the photon was annihilated and lost all of its energy. All of its energy went into the atom. And in the emission spectrum, because it goes from high end to low end, it loses energy. The change in energy of the atom is negative, and the energy of the photon is positive, and that just means it was created. So just remember that a photon always, really, if it exists, has positive energy. This is negative, is just talk about if it's created or destroyed. So we can say this. We know the Bohr's equation for the change in energy of an atom when it absorbs or emits energy. And we also know that that energy can be in the form of a photon, and the energy of a photon is hc over lambda. So if we set these two equal to each other, we have an equation that relates the energy of an electron in an atom, or the change in energy, to the wavelength of light that's absorbed or emitted. And we'll use this right now. So, for example, we want to know what the wavelength of a photon of light is in nanometers that must be absorbed by a hydrogen atom for its electron to transition from n equals 1 to n equals 3. So it's going from n equals 1 up to n equals 3. That means that n final is 3 and initial is 1. So we can use Bohr's equation for the change in energy of an electron in the atom, right here. Because it is hydrogen, Z is 1, so don't have to worry about it. N final is 3, so 1 over 3 squared minus 1 over 1 squared. Plug in, we get a positive energy, 1.936 times 10 to the minus 18th joules. And the energy of the photon that's absorbed is just hc over lambda. It's going to be equal in magnitude to this guy right here. Now to find the wavelength of the photon, we just solve this for lambda, cross multiply. And h, you guys know what h is. C, the speed of light. This is the energy we got right here. Joules cancels. Seconds cancel. And we get meters. So 1.026 times 10 to the minus 7th meters. We wanted nanometers, so we just divide by 1 times 10 to the minus 9th, and we get 102.6 nanometers. So when that hydrogen atom that's in the n equals 1 state, the electron's at n equals 1, when it absorbs a photon with wavelength 102.6 nanometers, it will go up to n equals 3. It won't stay there, it's going to eventually fall back down, but that's another story. So here's another example. Let's say we want to find out the wavelength of a photon in meters that's required to ionize a lithium 2+ ion that's in the ground state initially. So remember, ionize means to completely remove that electron, so n final is infinity, and 1 over infinity squared goes to 0. And this is a hydrogen-like atom because lithium with a positive 2 charge only has 1 electron left, so it works. So the change in the energy of the atom, the ionization energy, remember, is just Z squared. Now Z is 3 because lithium has 3 protons. 9 times 2.178 times 10 to the minus 18th joules over n initial squared. N initial was 1. Okay, if it was something else, we'd have to put that number in here. plug it in, and we get this many joules. Once more, solve for the wavelength of the photon, hc over lambda. Cross multiply, and we get 1.013 times 10 to the minus 8 meters.